Hello students, today we will read about Gauss's law. In the previous class, we have learnt about electric flux and we have defined electric flux as psi equals to 1 upon epsilon naught times the charge enclosed by a given surface. So the Gauss's law have a relation with this electric flux. With the help of Gauss's law, we define electric flux in a given Gaussian surface. The Gaussian surface is a surface which we use to describe Gauss's law. Gaussian surface. It is a imaginary surface. We have to imagine or we have to draw it. It's basically on us what sort of surface we want to take. It can be a regular or it can be irregular. And for any surface we can define Gauss's law. Now let's get started with the Gauss's law. For understanding the Gauss's law and deriving the formula, we have taken one sphere. This is the sphere which we have taken, which is having radius of r, and there is a charge q placed at center. Okay. Then for understanding, like in the previous class itself we have seen, this sphere is having a continuous trail of charges. The charges present over here are not discrete charges. Continuous charges. So we can define continuous charges by taking a small area element on the sphere. So this is the small area element which we have taken on the sphere, and the amount of small area element is del S. Electric field due to charge Q is alone radius vector and del S is also alone R. Okay, del S is also alone R. See over here, this is the radius. From Q to the surface is the radius, and from this radius this electric field is moving in this direction, and our normal to the surface, the projection of surface vector is also along this line. So here E, S and R all are parallel, and the angle which they are subtending with each other is 0 degrees. So these are the basic things which we have considered to derive the formula. Now let's come to the content over this place. Let us consider the total flux through a sphere of radius r which encloses a point charge q at its center. Described already, point charge is at its center and the radius is r. Let's divide the sphere into small area elements. Flux through an area element del S is given as del psi equals to vector of E dot vector of S. Here for the electric flux we also have seen it is a dot product of electric field and area vector. So when we remove this dot product, we get Es cos theta. So if our S is a small element, it can be written as E del S, and this can be increased as dLs cos theta. Since the magnitude of a unit vector is 1, okay, fine, we forget over here. From the help of Coulomb's law, we found out the value of E. What is it? It is 1 by 4 pi epsilon naught into Q upon R square. So and in the vector form, we have to add the R cap. R cap is a directional vector or a unit vector with magnitude 1, but it provides us direction. For defining the direction for this much of the magnitude, we use our unit vector, that is R cap. So here we have substituted the value of E from the Coulomb's law, and this is the del S as such. Here R cap dot del S are showing a relation of dot product, and when we will go ahead, we can simply remove this vector format. See, this shows these are in vector relation, so we can remove it as this is having magnitude of 1 dot implies cos theta. Like if we are removing dot product, we have to multiply this with cos theta into cos theta. As I have already explained over here, they are parallel and the angle they are subtending is 0. So cos 0 equals to 1. So we will introduce this value over here, and we will get R dot del S, R cap dot del S as del S only, but this is a value. This is just showing us magnitude. Since the magnitude of unit vector is 1, total flux through the sphere is obtained by adding up flux through all the different area elements. We will add up all the area elements. We have taken one small area element. We can take many such area elements like del S1 plus del S2 plus del S3 and so on up to del Sn, and if we are adding it, it will give us area of the whole sphere. We will see it in the next step. So let's see only this one. So here the flux, when we are adding up all the surface areas S1, S2, S3, everything, see all del S we are adding up into Q 4 pi epsilon naught R square into the area. Okay, we are getting the total flux. Del xi denotes flux for del S, whereas xi denotes flux over whole surface of sphere. Okay, since each area element of the sphere is at same distance r from the charge, we can say this value will remain same because r square, the value of r square is equal in all the cases. See, this is our sphere, and sphere have equal radius from the center to its surface, and at center we are placing the charge. So the position vector for any point on the surface of the sphere will be equal. So we are taking that here and only summing over the small area element. This remains constant for any point on surface from center where our charge is kept. And then the area, these small area elements are being summed up to find out the whole surface area. Now after summing up, this area becomes only S, and this value comes as such downwards. So xi, the total flux on the sphere, equals to Q by 4 pi epsilon naught R square into S. Now S is the total area of the sphere. From your previous classes, you may be aware that surface area of sphere is given by 4 pi R square, and volume of sphere is given by 4 by 3 pi R cube. Though this value is not needed here, still I am reminding you, because maybe when we are solving any question, we may need this particular value. Here the only value which is required is this value, 4 pi R square. Now this area is around 4 pi R square, and we are substituting this value in our previous formulae. Substituting it in previous equation, we'll say it equation because it's still not a formula. So after this was our constant, and this is the surface area of the sphere. We introduce it. Now see, 4 cancels 4, pi cancels pi, and R square over here and R square over here get cancelled. What are the things we are left with? We are left only with Q epsilon naught. We are left only with Q epsilon naught. So what does it give us? It gives us xi equals to Q by epsilon naught. So while reading about the electric flux, we have predefined electric flux as the flux is the amount that is equal to 1 by epsilon naught into the charge carried by that surface. Above equation is simple illustration of general result of electrostatics called Gauss's law. We state Gauss's law without proof. Electric flux through a closed surface S is given as Q upon epsilon naught, where Q is the total charge enclosed by the surface area S. Surface area S. So this is a general result, and this result is termed as Gauss's law. This result that flux through a surface is 1 by epsilon naught the times the charge enclosed by the surface. The law implies that the total electric flux through the closed surface is 0 if no charge is enclosed by the surface. In case the charge enclosed by the surface is equals to 0, then What will be the value of xi? What will be the flux? 0. It will be 0. But we'll consider a second case. We will consider a second case. In this case, someone told us from the given surface we find no flux coming out. In the surface there is 0 flux, the value of xi. So vice versa, we can state that this surface do not contain any charge. The charge contained by this surface is 0. In case charge is 0, xi will definitely be 0. But somewhere someone is telling us the surface isn't giving us any flux. We can conclude the surface do not contain any charge. Now we will understand how valid this particular concept is. For this we have considered this cylinder. See over here the diagram of this cylinder and try to understand diagrammatically what exactly is happening. In this we are having three surfaces. One is this surface, circular. This is other surface which is also circular. Surface 1 and surface 2 are circular in nature. So what will be their surface area? It will be pi r square if r is the radius of the cylinder. The other one is this curved surface area. This curved surface area S3. S3 is curved surface area, and this is given by pi r h. So this is actually basically not needed over here, the values, but see the electric field is moving in this direction. I'll take a red ink to explain this concept better. See, this electric field is moving in this direction. Area vector for this is also in the same direction, S2. So flux from this surface 2, flux from surface 2 equals to E dot S2. Now electric field is going in this direction and the area element of this phase 1 is going in this direction, opposite, in opposite. So when these two lines are oppositely oriented, it means these two electric field and area are anti-parallel and hence are making an angle of 180 degrees, and therefore cos 180 degrees value we need to find, which is -1, So flux from the surface 1 will be E dot S1, which will give us minus ES1. Here surface 1 and surface 2 both will have same value equals to pi r square, because this is our uniform cylinder, and cylinder have both the circular ends equal. If both the circular ends are not equal, then cylinder tends to form a conical structure. So S1 is equal to S2, S1 equals to S2. Now we will go to Xi3. Xi3 is the flux coming out of surface 3. This will be also given as ES3. Electric field having a dot product with the surface area 3. Now the surface of this curved area, surface area element or the surface vector goes up. S goes up. and our electric field line are going in this direction along the positive x-axis, or as you can see my paper, it is in the positive x direction. So what do you think is the angle made over here? It is the 90 degree. See, I'll write over here, electric field and surface area make an angle of 90 degree. Therefore, theta equals to 90 degree. Dot product is defined by cos, hence cos 90 we need to find, and cos 90 is 0. So 0 multiplied by anything, what it will give? It will give us a value of 0. Now come to the right down corner, left down corner, we will find xi total. Xi total, flux total will be given by flux from surface 1 plus flux from surface 2 plus flux from surface 3. From surface 1 it is minus ES. See, S1 equals to S2 equals to S. Let us give a common name. And xi2 is ES and xi3 is 0. These two are equal and opposite will cancel out each other, and then xi total value is coming around 0. So this is a uniform cylinder which do not contain any charge, and hence flux coming out of this cylinder is 0. We have proved if a Gaussian surface or any surface under the consideration do not contain charge, will not give us any sort of electrical flux. The electrical flux coming out from such a surface will be 0. Now I'll read out the points. See, consider a closed cylindrical surface having its axis parallel to electric field. Electric field is uniform. Total flux to the surface is xi, given as xi1, xi2 and xi3, where xi1 and xi2 represents flux to the surface 1 and 2 of circular cross section of the cylinder, and xi3 is the flux through the curved surface, curved cylindrical part of the closed surface. Normal to the surface 3 at every point is perpendicular, hence perpendicular to E. Hence the flux from the surface 3 is 0. The last line defines flux from surface 3. Now outward normal to 2 is alone E, while the outward normal to 1 is opposite to E. In this case, from surface 2, E and S are in the same direction, whereas surface 1, E was in this direction, whereas S was in this direction. Therefore, xi1 equals to minus E S1 and xi2 equals to plus E S2, and hence S1 equals to S2 equals to S, as explained already. How did this come? I have already explained. Surface area from one curved surface equals to surface area from other. Both are circular. Both have same radius. R1 equals to R2 equals to R, and then S2 equals to S1 equals to S, and it is given as pi R1 square equals to pi R2 square, commonly which can be written as pi R square. So both are equal, where S is the area of circular cross section. So the total flux is 0. Total flux is 0. We have derived it in the previous slide. How come we get to know the total flux is 0? Now let electric flux through the closed surface is 0. We conclude that the total charge contained by the closed surface is 0. Once it is proved that psi equals to 0, we can say that Q in the given closed surface is 0. Great significance of Gauss's law equation is that it is true in general. Gauss's law equation. What is Gauss's law equation? As we have already seen, it is psi equals to 1 by epsilon naught into Q. And if psi equals to psi equals to 0, flux equals to 0, charge contained by the Gaussian surface will also be 0. Charge contained by Gaussian surface will also be 0. They say that it have a great significance. Gauss's law equation have great significance, and according to them the great significance it is true in general. See, previously we have said without proving it, without mathematically solving it, no mathematical solution. And we have proved that the flux is the amount of charge multiplied by 1 upon epsilon naught. So whenever we take a small area element, it is true for that. If we take uniform area element, let it be a circle, a triangle, or rectangle, or square, or any other hexagon, pentagon. Okay, if we are taking any of the defined uniform area element, it is true. If we are taking a non-uniform shape of Gaussian surface, it is true for that also. You can take a surface like this, and you can, from this surface, you can define Gauss's law. We can define it for such a surface also. That's why it is said to be of great significance, and it is true for each and every sort of Gaussian surfaces. Some important points regarding the Gauss's law. Once we are reading the Gauss law, it is very much important to know the applicability of our Gauss law. Where it's applicable, why it is applicable at that point, and where it is not applicable and why it is not applicable at that point. The applications and applicability of a law is very much important to be known. So these important points are all about the Gauss's law. See the point 1. Gauss's law is true for any closed surface no matter what its shape or size is. It is true for closed surfaces. So for what it is not true? For the open surfaces. A surface should be closed. We always miss to read what is the meaning in between the two written lines. So when they are saying, when they are pressurizing the thing that any closed surface, it implies that we have to think about the opposite of closed surfaces. that is the open surface. Okay, so that should be taken in account. Next, the term Q on the right side of Gauss's law equation. I'll write the equation here so that it is easy for us to understand what they aim at saying. Q equals to 1 upon epsilon naught into xi equals to 1 upon epsilon naught into Q. That is the Gauss's equation. This is the right side, this is the left side. Okay, so this we are talking about this Q includes the sum of all charges enclosed by the sphere, enclosed by the surface of the sphere. This Q includes all. If this is our sphere and this sphere is having Q1, Q2, Q3, Q4. So while writing the flux, we will write it as xi equals to 1 upon epsilon naught into Q1 plus Q2 plus Q3 plus up to Qn, whatever number of charges are present in the enclosed system. The charge may be located anywhere inside the system. It is not compulsory for the charge to be present at exactly center or any other defined position. Charge can have any location inside the sphere. Third point, when the surface is so chosen that there are some charges inside and some outside, electric field is due to all the charges, both inside and outside. The term Q on the right side of Gauss's law, however, represents only the total charge inside the S. Now understand this. This is a Gaussian surface. It contains Q charge inside, Qn, and Q charge outside, Q out. So electric field defined for this system will give us K, Q inside and Q outside will depend upon these, upon the r square, the distance. Okay, whereas the flux will give us 1 upon epsilon naught into Q in. So this is our Gauss's law. This Gauss's law is defined only and only for the charges which are present inside, but this Gaussian spherical surface will have electric field due to the charge present outside also. So these are two different components, electric field and flux. These are two different components. Electric field is for any surface or for any point. Electric field is due to all the charges in the surrounding, far charges, near charges, inside the system charges or outside the system charges. But flux is a resultant of only and only the charges which are present inside the closed Gaussian surface. Now coming to the point number 4, the surface that we choose for the application of Gauss's law is called a Gaussian surface. If we choose any Gaussian surface and apply Gauss's law need to be taken care that the Gaussian surface do not pass through any discrete charges. So what is it? Discrete charges. This is because electric field due to the system of discrete charges is not well defined at the location of any charge. However, Gaussian surfaces can pass through a continuous charge distribution. So see why they are saying that it should not pass through the discrete charges but can pass through the continuous charge distribution. The reason for it, as they have given us, is that discrete charges is not well defined at the location of any charge. These discrete charges are not defined properly at any location, like their position is not certain, position not certain. They have electric fields which are disoriented. But when we go for the continuous charge distribution, these charges are present near to each other and look like a trail, and defining their position is quite simpler as compared to the discrete charges. Position defining is simple. Hence, Gaussian surface can pass through a continuous charge distribution but not through discrete charges. Now, Gauss's law is often useful towards the much easier calculation of the electrostatic field when the system have some symmetry. This is facilitated by the choice of a suitable Gaussian surface. Like we will be reading the application of Gauss's law. Application of Gauss's law in next class. In that we will see that we are taking a uniform and very much defined surface. Why so? This is here in the point number 5. We aim at taking a system which has some symmetry, because for symmetrical system it is quite easy for us to do the calculation or to define the Gauss's law. Symmetry in system. Finally, Gauss's law is based on the inverse square dependence. This is also based on the inverse square dependence on distance contained in the Coulomb's law. How it is possible? Like xi equals to 1 by epsilon naught into q. Similarly, we have seen xi equals to E del S, where E is dependent upon R square and xi is dependent upon E. So, by this relation, xi is also dependent upon R square, and here this is equals to 1 by epsilon naught into Q. So, directly or indirectly, Gauss's law have relation, Gauss's law have relation with inverse square law. Any violation of Gauss's law will indicate departure from the inverse square law. So, this is actually not in this way, like anything which is not following the inverse square law will not follow the Gauss's law, but it is defined as any system not following Gauss's law will show deviation from inverse square law 2. So, Gauss's law gives a proper definition and it's properly dependent upon inverse square law. So, this actually justifies or helps the Coulomb's law's stability, shows that Coulomb's law is a very fundamental law and it is extremely true for our electrostatics, like a helping hand for Coulomb's law in electrostatics. statics. So this is all about the Gauss's law. In the next class we will read application of Gauss's law, and before ending this class we'll just summarize up what we have read in today's class. Okay, so we'll just summarize it. So in our class of today we have read about Gauss's law. Okay. For understanding the Gauss's law, we have taken a spherical body which is containing a charge q at the center and having a radius r. At the position of r, at radius r, we have considered a small area element del s. For this del s, the electric field is uniform and it is going in the direction of r. It is along the direction of r position vector, and this del s is also having its vector along the r, so E and S are along r vector. They make an angle of 0 degree, cos 0 equals to 1, cos 90 equals to 0, and cos 180 equals to -1. So these are the values we need for our discussion. So we have taken this Gaussian surface, charge at center, q at center, and now we define the flux. Due to this charge, flux due to charge q inside the sphere, for given small area element del s, small area element del s. So it will be defined as xi equals to E vector point dot del s. So from Coulomb's law, E is defined as vectorially. ठीक है, it's not simple scalar. We are defining E with respect to the vectors 1 upon 4 pi epsilon naught q upon r square into r cap. R cap over here is unit vector along E, R and S all. Then this xi will become 1 upon 4 pi epsilon naught q upon r square r dot del s. As we have said, these are alone s in E, r cap is alone s in D, therefore r cap, this will be given as r is unit vector, so 1 into del s cos theta is 0 and it will turn out to be only del s, so xi equals to 1 by 4 pi, and this is the xi from the small area element. So from the small area element, small flux will come out, epsilon naught q upon r square into del s. Now summing all such area element for the sphere under the consideration So del S1 plus del S2 plus del S3 up to del Sn equals to S. That is the total surface area. Total surface area. Now our xi will become del xi1 plus del xi2 plus del xi3 plus dash 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 till del xi n will give us xi, that is total flux. Total flux. So it will be xi equals to 1 by 4 pi epsilon naught into q by r square into s. Here s is surface of this sphere which have value equals to 4 pi r square. So it will come around 4 pi epsilon naught into q upon r square into 4 pi r square. 4 cancelled out with this 4, pi with this pi, and r square with this r square. What is the value we have left with? Q upon epsilon naught. So xi total comes around q, charge contained by the sphere divided by the epsilon naught. So this gives us the Gauss's law, which we have seen even while understanding what is electrical flux. Now, after deriving the electrical flux, we need to know its applicability and important points for Gauss's law. So, first thing, if xi equals to 0, q equals to 0 and vice versa. What does the vice versa here implies? If system do not contain any charge, flux from the system is 0. First point. Second, Gauss's law is applicable for closed surfaces. Flux is given by charges present inside Gaussian surface. Gaussian surface. What is Gaussian surface? A surface for which we are defining Gauss's law. Surface for which Gauss's law is defined. Fourth, E is due to charges present inside the surface plus charges present outside the surface, but xi is always due to charges present inside the surface. It do not account for the charges present outside the surface. Then symmetrical Gaussian surfaces. Gaussian surface gives us easy calculating ways. Easy calculation. So if we are going for a calculative thing, we need to take some symmetrical Gaussian surface and it will be easy for us to do the calculation. And then the last and the most important, Gauss's law follows inverse square law. Follows inverse square law, which is very much important. If something is not going according to Gauss's law, we can say that it is deviating from inverse square law too. So that's all for the today's class. We have learned about the Gauss's law and important points about the Gauss's law, and we have summarized our topic within like 8 minutes. And within these 8 minutes also, if you just go through this after learning the slide, all these slides, after learning that, if you go through the summary for 2 times, you will be able to understand the whole concept of Gauss's law. It is very much simple. We are just defining the flux, and always make sure of this one point, that when this surface is taken, the charge inside it influences only flux, but the charge present over here will influence the electric field. So whenever someone asks you what is the electric field on this sphere, consider the charge outside and inside. But whenever the concept comes about the flux, never and ever include the charge which is present outside the Gaussian surface. Only and only the charge inside the Gaussian surface should be considered when we are calculating the flux. This is the most important point, and here I have seen students making mistakes. So don't make such mistakes. Okay, so that's all for today's class. We'll meet in the next class with the application of Gauss's law. Have a good day.